fun, but man, it was a mess. We had so many busted pipes in the area. We didn't have any in our house, but it was pretty bad. Okay, so today is going to be interesting, I hope. We're talking about state functions, a little bit about state functions and what we mean by that word state function, and then the physical properties of substances. So we're going to hit a lot of the things that you're familiar with, even if you didn't know what words to use to describe those. So today you'll learn the words to use to describe some of the phenomena that you're very familiar with. And so let's first talk a little bit about state functions. So there's this difference between inexact differentials and exact differentials, and that's a big deal with state functions. We'll show an example of an exact differential, but inexact differentials are things like Q and W. They're not state functions, and therefore they are inexact differentials, which means they can't be simplified to delta Q and delta W. Notice when we did the isothermal reversible expansion for W, we had to do the integral. Okay, we couldn't just take the initial state and the final state and do the difference. Okay, so that's another way to say that their integration is path dependent. And whether you drop down to a constant pressure and expanded, or you followed the little isotherm, you got different amounts of work. The initial state and the final state were the same, but you got different amounts of work because they were a different path. One dropped down to the external pressure and went straight across. The other followed that curve down. And so, now, exact differentials, the internal energy, pressure, temperature, volume, enthalpy, those are state functions. Part of what we mean by state functions is that they are their differentiation is not path dependent. Okay. They also have exact differentials, which means the order of differentiation doesn't matter. So we'll see that example on the next slide. So the integration is not path dependent, and we can just take the initial state and subtract it from the final state to get all of our deltas. And so the example then is the take-home lesson is that most integrals can be simplified by these deltas. So here's what I mean by exact differentials. So if we have this equation of state right here, it's pressure, which can be written as a function of volume and temperature, and we'll just say that the number of moles of substance is constant, okay? And so we can write that in terms of its molar volume. This is a very common practice. So this molar volume is liters per mole. Whenever you see that VM, that's liters per mole. Or sometimes it's milliliters per mole if it's in a table, which look at the units on the table. But anyway, liters per mole in terms of the ideal gas law. And so really this pressure is just RT over VM. So there's just two variables. And if we're going to do the total differential for this, what we want to do is we want to see how it changes when both temperature and volume change. So we have to differentiate with respect to temperature and volume. Now, in almost every case, I'm trying to go back through all of my math, we would look at partial derivatives. I don't know if y'all did that. I think it's part of multivariable calculus, so that would be in our schooling, Cal 3. Okay. And so that's why my differentials are written funny. This little funny shaped D means a partial derivative, and we put down here the term that's held constant. And so if we do the derivative of this function with respect to volume, we treat temperature as a constant. And then if we do the derivative with respect to temperature, we keep volume as constant. And so I've substituted this state function now for this RT over VM, and I'm going to differentiate this with respect to volume first, keeping temperature constant. All right, so this is 1 over V, or V to the minus 1 power. And so then I bring that minus 1 power down front. So this is your minus 1. And then I drop the exponent by 1. And so now it's V to the minus 2. So now it's in the denominator squared. So you see the derivative? Just a little review of calculus. Okay. And I've done this first operator. So this one is done. And now I do the second operator. So if I do temperature, then I look at this and I differentiate with respect to temperature. It's this coefficient times temperature to the first power. Okay. And so then I bring down the +1, and then now it's temperature to the 0th power, or 1. So temperature disappears, and I get the coefficient in front of temperature. So this is the total differential of the ideal gas law. But notice I had to make a choice at the beginning. I chose to do volume first and temperature second. See that up there, the order of operations? Over here, I swapped the order just to see if they're the same. So if I do temperature first and volume second, then I get the R over Vm by differentiating with respect to temperature. And now I differentiate the volume, so it's volume to the -1. So the -1 comes out, and it's volume now to the -2. And so I get the same answer. And so this is what we mean by an exact differential. It's not path dependent, right? I can differentiate with respect to temperature, then volume, or volume, then temperature. I get to the same spot. I get the same answer. And so the order of differentiation doesn't matter for exact differentials. Okay. Now let's look at these thermodynamic quantities and the different properties that, like I said, you may be familiar with, but you just don't know the terms for them. So there's a property called volumetric expansion coefficient, and that accounts for the change in volume when you change the temperature. So that makes sense. You have a gas in a balloon. What happens when you increase the temperature? The balloon gets bigger, so the volume expands, the temperature goes up, so it's a positive correlation, and then it goes down when the temperature cools. That's going to be it's going to be the term beta. So here's a second use of the character beta in this course. Then you have the isothermal compressibility, which accounts for the volume change with respect to pressure. So if you press on a balloon, it's gonna shrink. Okay, if you pull a vacuum in the room, that balloon's gonna grow. Same with materials, and so we'll look at the different materials that we see. So that's kappa with a lowercase t, and then that's going to be a negative sign, an opposite correlation, because if I increase the pressure, the volume shrinks, and if I decrease the pressure, the volume expands, and so it's the minus sign representing that. And then we have the Joule-Thompson coefficient, and this is pretty cool. This is the nature of refrigeration and heat pumps, because if I change the pressure, then the temperature will change. And so this one is not so easy to predict in terms of whether it's going to be positive or negative. Sometimes in certain pressure regimes, you drop the pressure and the temperature goes up. In other places, you drop the pressure and the temperature goes down. So that one's really, that one's very interesting. And then there's this one called the internal pressure, which I really hate that name, because if you think about pressure, what is pressure? It's a Newton per square meter, right? Newton per square meter. If I multiply that Newton per square meter, so I have a Newton, let's just do this over here. And then I multiply that by a meter over a meter. That's totally legal, right? Because I'm just multiplying by 1. All right. So a Newton times a meter is a joule. And I have a meter times a meter squared, so that's meters cubed. So this is an energy per volume. So this really is what we call the cohesive energy density. It's how much energy is in the intermolecular attractions in a particular volume of the liquid. Isn't that cool? Right? It's how much energy is in the intermolecular attractions per volume. So how could that be used? Well, I could use that to determine if blends would mix and be miscible. I could use that to determine if something would be soluble. So think about it. When I mix two things, I'm taking liquid A and liquid B, and I'm breaking. One way to do this is to break all of the intermolecular attractions on liquid A and make a gas. Break all the attractions on B and make a gas. Let the gases mix. That's going to be spontaneous statistically because they take up more space, and then letting them condense. Do I get as much cohesive energy back when they condense as it took to evaporate both liquids in a pure state? So I could compare the internal pressure or the cohesive energy density of the mixture to the pure substances and determine if this is going to be a miscible solution. And so we'll get into that. That's the basis of solubility parameters. So the Hansen solubility parameters, which we'll cover, I don't know, in like week 9 or 10, are based upon this particular substance, but it has such a misleading name, internal pressure. And in fact, all of the books that list the Hansen solubility parameters or other solubility parameters use pressure units. And whenever I write papers and articles, I always change it over to joules per meter cubed or joules per milliliter or something of that sort, so that people can think about how much energy I have in a particular volume of a substance. So let's go through these individually. So let's talk about the volumetric thermal expansion coefficient. So this accounts for the change in volume with respect to temperature. And sorry, that's not KT to the -1 this time. It's just beta is the thermal expansion coefficient. It's alpha in some books. And so what do we expect for an ideal gas? So this is the thermodynamic definition of beta. So it's 1 over V, and it's an operator. So it's the change in volume with respect to temperature at constant pressure. So we could take that beta and we could operate on our state function, our ideal gas. So we can take this and we can differentiate volume. So we have this written in terms of volume. So we can look at the change in volume with respect to temperature, holding pressure constant. So that's what we're doing here. We set this up. So we're taking the derivative of nRT over P with respect to temperature. So that's pretty straightforward. T is up here in the numerator, so it's just nR over P. We have this 1 over V in the front, kind of help with the units. So this is our beta for an ideal gas. If we had the state functions for a liquid or for a solid, which would be different than the ideal gas law, then we could do this for liquids and solids, different substances and so on. So if we put in all of our units for a mole and so on, and 1 atmosphere pressure, in the gas constant, etc., this is what B turns out to be. Okay, 0.082 per Kelvin. So what does that mean? Well, that's in terms of this magnitude of these up here, like 10 to the 4th beta, etc. So this is 820 compared to these numbers over here in the table. So it's about 8.2% per Kelvin. So that's for an ideal gas. So if I change the temperature 1 Kelvin, the gas expands 8%, which is a pretty big expansion compared to the liquids and solids. So let's look at the table that has the information for liquids and solids. First of all, let's figure out how to read this table because it has a 10 to the 6th beta up here. And I'm not sure if you can figure out that very easily. So that has a number of 18.9. And here we're at, 0.082, how does that compare to 18.9? Well, we need to take into account this table label. And so in any table, what you've got is the label of the table is equal to the number. The label at the table is equal to the number. So you can set that up here at the top. So 10 to the 6th beta is equal to 18.9. And so when you solve for beta, it's 18.9 times 10 to the -6. That's what beta is. And this is 8.2 times 10 to the -2. So this expands, 4 orders of magnitude more than a solid, which makes sense, right? You change the temperature of a solid 1 degree, it doesn't change by 8% in terms of its volume. That would be shocking. Like if the table in here, the tabletop changed 8% for every degree, it'd be pushing everything around. It would be scary, actually. It'd be a scary place. If all our solid objects change that much, like the gases do. Okay. And you can look at the numbers here. Look how distinct the different metals are. So silver, aluminum, gold, copper, they change by quite a bit. In fact, down here at silicon, silicon's only 2.6, and magnesium's 24. So magnesium expands and contracts 24 times more than silicon. Probably wouldn't be good to make our computer chips on top of magnesium, because as the machine heats up and so on, it would bust all the circuits, because you've got all of your traces and everything. And if the substrate material is expanding, 24 versus silicon, which is only expanding 2.6, then it's probably going to cause trouble with our circuits. Liquids are 2 more orders of magnitude. So this is over here, mercury is 18.1 times 10 to the minus 4, whereas a solid is 10 to the minus 6, a liquid is 10 to the minus 4. So it expands a lot more than a solid, but not as much as a gas. These are things you learned in elementary school or maybe middle school when you first started learning about states of matter. You learned that gases were compressible and expandable with temperature, and solids and liquids were not. Now, we said they weren't. They are a little bit. Okay, makes sense? Now, this is the expansion and contraction with respect to temperature. Notice on the liquids, so 18, let's see, here's methanol, 14. Here's, let's see, this is ethanol, 11. So like an alcohol thermometer would expand 11.2, but mercury would expand 18, so more. So a mercury thermometer is going to be more sensitive to temperature changes. It's going to give you a bigger range of motion based on temperature. And here's water. Water would not make a very good thermometer compared to mercury, 2.04. Now, it looks like the solid expands quite a bit. This is 1.6 times 10 to the minus 4 compared to these solids over here. Now, this is a really important property as well for dentistry. Why would you think that? So the thermal expansion coefficient. So the volumetric thermal expansion coefficient. So I drill a hole in your tooth and I fill it with this substance, and then you go and drink something hot. And if it expands, it's going to change the dimension of that tooth, and your nerves are going to notice. So there's 2 things that work. This is one of them. The other is how much they conduct heat. And so if it can conduct temperature down to that nerve, then you see a huge signal in your mouth. And you're like, oh my gosh, I'm hot and cold sensitive on that tooth. But another property would be the expansion and contraction with temperature. You wouldn't want it to crack the tooth if it really expanded a lot. And so you can find mixtures of substances and alloys that have a really low volumetric thermal expansion coefficient. And so that's what you would want for dentistry and dentist fillings. You'd want it to be hard, inert, non-toxic, and to have a low thermodynamic property of expansion with temperature. Okay, let's talk about compressibility. So this is the isothermal compressibility, and it's the change of volume with respect to pressure. And so same kind of thing, we can differentiate the volume with respect to pressure and keep the temperature constant. So now pressure's in the denominator. So it has a negative sign out front. When we differentiate it, this pressure is in the denominator, so P to the minus 1. The minus 1 comes down and cancels that minus sign, and we have P to the minus 2. So we have this. And so here's our isothermal compressibility. So for a gas, we put in those values, it's about 24.1 per bar. And so you can think about the if you change the pressure of a gas by 1 atmosphere, the volume is going to change by 24. So 24 units of change, like 24 liters per 1 atmosphere. And that's roughly what we see in terms of the volume of 1 mole is, 24.4 liters at room temperature at 1 atmosphere. If you were to double that pressure, you would shrink it down. And so let's look at some of these properties here. So it expands 24.4 times per atmosphere. And up here, the solids are only 1.3 times 10 to the minus 6 per bar. And a bar and an atmosphere are very close. They're like 1% different. And so these are, some of these are more compressible than others. Here, nickel's not very compressible at all. Sodium's very compressible. And other interesting properties, looks like the alcohols, like here's ethanol, very compressible. It changes a lot. And this is still 10 to the 6th? Yeah, that's still 10 to the 6th. So liquids and solids have very similar compressibilities. And they're pretty small compared to a gas. And so we would say that a liquid, a solid is not compressible, whereas a gas is. Now, this is not what you want if you're trying to do pneumatics or hydraulics. That's the difference between pneumatics and hydraulics. If I want to push a button with a gas, I can run a tube of gas over to the button, and I can pressurize it on this side, and it can push on the button there. But because the gas is compressible, I've got to push a lot harder, and it's slower. So I've got to push a lot of gas in there, and it's real spongy. It's being compressed, and then it'll push the button. Okay, but if I had a hydraulics and I filled that tube with liquid, all I have to do really is just to put in the force of pushing the button at this end, and that force is transmitted all the way over to the button, and it pushes the button. And so it's much more efficient to use a liquid to push things than a gas, because a gas will push things, but it's real spongy because it's compressible. So if I wanted a really efficient hydraulics, I would pick a liquid that had even a lower isothermal compressibility, and then it would more efficiently transmit pressure. So when I say push a button, it could also be push a piston. So in all of your heavy equipment where you're scooping up things, those are moved with liquid. You have a diesel engine that's turning a pump that's pressurizing the hydraulic fluid, and then you have these little valves, and you just push that fluid into these pistons. And because that fluid's not compressible, it's very efficient at transmitting power from the pump through the valves into those pistons. And I mean, that's how we build things. You can see how much power is in these devices when you go to a construction site. That's all being done with liquids using this lack of compressibility to its advantage. Now the Joule-Thompson coefficient. This one's really crazy. I mean, we've probably experienced this, but probably less so now. When I was a little kid, we really didn't have like TMI here. We really didn't have the deodorants that we have now. The sticks and so on. It was all spray. It was like Right Guard was the one, and so you would spray that on, and as a young teenage boy, the parents are like, man, you need some deodorant. Okay, so I never understood. You spray that and it's cold. I don't know if you've ever sprayed, maybe, I don't know if hairspray does this or what are other things that spray tan stuff or spray sunscreen, maybe you've used that. Anyway, when you spray it, it's cold, but it's not cold in the can. You ever wonder about that? As a kid, I was not a scientist, but I was curious. I was like, why is it cold? Does it make sense? I mean, why? It's not cold in the can. You spray it, it's cold. So what's going on? It's not just that it's wet. Yeah, it's this. It's the Joule-Thompson coefficient. So it's high pressure in the can, low pressure out. And when you spray that, the gas cools. Now, why might that be? Well, in the can, you've got all these intermolecular attractions, that internal pressure, the cohesive energy density. When it comes out of that nozzle, those bonds are broken. They're not bonds, but they're like London forces and polar forces and hydrogen bonding. So you're not going to pull those molecules apart without paying the penalty in energy. So the energy of those molecules has dropped. And how do we measure energy? We measure with temperature. So the temperature of those molecules drop. And how much is the Joule-Thompson coefficient? So how much temperature it drops per unit of pressure is one of the ways to measure the Joule-Thompson coefficient. So see, we are differentiating temperature with respect to pressure. So if pressure goes up, temperature may go up or down, and so on. It's how does the temperature change with change in pressure at constant enthalpy. Now that's kind of a weird one. I don't see enthalpy in my nRT over P state function. So we might have to do some fiddling here. You could also look at it as delta T over delta P if the partial is small. It's another way of saying that the slope is constant over a short range of pressures, and it really simplifies these problems. Now we have up here you have the Joule-Thompson coefficient, which is technically at constant enthalpy, but then you also have the isothermal Joule-Thompson coefficient. So those are very different terms. So just make sure that you are paying attention to whether it's the isothermal Joule-Thompson coefficient or the Joule-Thompson coefficient. And this is actually how that mu is measured today. So this isothermal Joule-Thompson coefficient is different from the Joule-Thompson coefficient by the heat capacity at constant pressure. And so it has units of joules per mole per atmosphere. So it's an energy change in terms of atmosphere change. So we change the atmospheric pressure or the pressure of the system, then you have a change in the energy. So let's look at it in terms of this three-dimensional plot of temperature, pressure, and enthalpy. The isothermal Joule-Thompson coefficient is shown here. You see the temperature, when something's isothermal, it's a particular spot on that temperature, right? And so in this curve of enthalpy as a function of temperature and pressure, you have the instantaneous slope right there, which is the change in enthalpy with respect to pressure at constant temperature. So it's heat in or out with the change in pressure. Does that make sense? Heat in or out with the change in pressure. Now the other one, the change in temperature with respect to pressure at constant enthalpy, that we can also show on the same diagram. So constant enthalpy would be, again, a number, it'd be a particular number on the enthalpy scale. Well, that's kind of hard to draw, but I'll try. So we come across and then we draw that line. It's kind of like a contour line on that curved surface. And so we pick a particular, as pressure changes, right? So we're going to get the slope of this line right here at constant enthalpy. So it's let me see if I drew it down here. Yeah, so it would be, in a two-dimensional plot, it would be this slope right here. Oh gosh, I can't do it. I've got to stare at it exactly. So it would be this. So I've drawn a projection of that curve down here and this instantaneous slope. You see it? And that's in the temperature pressure plane. And so we could change the pressure and see what the slope of temperature with respect to pressure is. And that would be the Joule-Thompson coefficient. And this would be the isothermal Joule-Thompson coefficient. So you see the little subscript T. And so this one, let's see, let me go back. Yeah, so the isothermal is this is the relationship between the two. So mu T is the heat capacity at constant pressure times mu JT. So this is an example of how we measure the isothermal Joule-Thompson coefficient. So this is the can of Bright Guard, the deodorant can. We've got over here, we've got the pressurized gas. And this is the low pressure. We have this porous plug called a frit. You've seen fritted glass, perhaps. Did y'all ever do any experiments where you did the filtration in a vacuum flask and you had the white, it's like a clear glass crucible with a white disc in the bottom? And Have y'all used Buchner funnels with paper? Okay, so the paper is got bigger pores, and you can get this fritted glass crucibles that they take tiny little micro beads of Pyrex, and they pack them in this small space, and then they warm it up to around 500 C, and it doesn't quite melt. It gets soft, and all those little spheres stick to each other. Now, you can really control the pore size by controlling the size of the spheres. And so they have 2 micron holes and 5 micron holes and so on. You can do the same thing with metal. So brass, steel, you can take these little spheres, pack them in a little plug, and then warm it up just below the melting point of that material, and those spheres will stick to each other and make a fritted filter. So this porous plug it's called a frit. So the gas goes through there, expands, and so you just set up 2 thermocouples and control the energy going to the heater, and the thermocontroller will put more or less heat into that heater until these temperature probes measure the same temperature. So it's a way to directly measure how much energy you have to put back into the gas to get it back up to the energy. So the temperature dropped because we stripped all of these intermolecular attractions apart, and then we use the heater to bring that gas back up to temperature. So we're actually directly measuring how much energy the gas lost by expanding. And so this is the Joule-Thompson coefficient. Also, if we don't use the heater, it cools. You can measure how much it cools. Okay. So again, we can use those that 10 watts in terms of how many joules per second. You've got the flow rate, so that's 6 moles per minute. You convert minutes to seconds, and then you have the pressure drop in atmospheres. You put all of these together using the units as a guide. And so we know that Joule-Thompson coefficient has units of joules per mole. So this is the unit we want, joules per mole per atmosphere. And so we use that to determine where we put all the numbers in the problem. So we had watts, 10 watts, so that's joules per second. We had a flow rate of moles per minute, and so we just needed to cancel those units. So 60 seconds per minute. And now we've got our Joule-Thompson, or isothermal Joule-Thompson coefficient. And so it's minus 20 joules per mole per atmosphere difference. So if there's a 1 atmosphere difference and it's flowing through that frit, it will lose 20 joules per mole. It's probably, I don't know. I don't know what to compare it to. I should go get the refrigerants and compare it to the refrigerants to see if that's a good refrigerant or a bad refrigerant. But what's going on in your house and your automobile refrigerators? You have a compressor, and it's expanding a gas through a tiny little orifice and creating a cold region. And then that cold region is got a lot of fins on it, a heat exchanger, and you've got a fan that runs your air through that heat exchanger, and that sucks the heat out of the air and it gives you cool air. So this is and so then if the heat capacity at constant pressure is 40 joules per Kelvin per mole, then you can find the actual Joule-Thompson coefficient, 0.5 Kelvin per atmosphere. So that's a way to sort of get it into terms of temperature. So it'll drop a half a Kelvin per atmosphere difference. So this is this Joule-Thompson coefficient. Really, there's certain pressure temperature ranges where it will actually invert. It will change sign. And so if we look up here where the Joule-Thompson coefficient is positive, then that's going to be a situation where it's cooling. And so all of these gray areas are cooling. And this is for nitrogen gas. And this is pressure in atmospheres. So, if we run the high pressure side up to 200 atmospheres, and we're, here's room temperature. We're right in this area here. The nitrogen's going to be cooling. Okay. If we run our compressor up to 400 atmospheres, then we're up here in this region, and it's not going to be cooling. So that's kind of strange, why in some pressure regimes it would be cooling, in other pressure regimes it would be not cooling. And then down here, where hydrogen, no matter what pressure range we are, at room temperature, hydrogen is going to be in the heating range. And so what would happen if a hydrogen tank developed a leak? So we're going to run our cars on hydrogen, right, because of the energy density. And so then we've got a hydrogen tank on board, and in that tank, we've got a big old tank of hydrogen on our car, and there's a tiny little leak there. Okay, that's a Joule-Thompson situation. High pressure, low pressure, it's expanding, and most of the time, like in this region, most things like nitrogen, we think about, they cool down when they leak. But a hydrogen in this situation, no matter what pressure we're at, that hydrogen is going to heat up right there at the area where the leak is. And so we want to keep it light. So a lot of times our pressure tanks for automobile applications are actually polymers, plastics. And so at that little pinhole leak, it's going to heat up and weaken the plastic, which is going to make the leak even bigger and even bigger. So hydrogen is the least compressible gas. It's a nightmare, and I don't want 9,000 psi of hydrogen in my car. Okay, so what about this inversion temperature? Think about it really high pressure. So this is a figure that you need to have in your brain. That this I would say memorized, but it's got to be deeper than memorized. This has got to be something that when you think of nature, this is one of the figures that is just a part of you and how you think about nature. This is the internuclear distance. Okay, it looks like a bonding Morse potential, right? Like a hydrogen chloride bond. The anharmonicity. We've seen this before with the vibrational levels, right? But this is not a covalent bond. This is the same behavior for polarity, hydrogen bonds, dispersion forces. Any molecule that gets close to another molecule will have some sort of interaction like this. There'll be a region where the electron cloud starts oscillating in concert, and it's sticky and it's attractive. But if you get too close, it's not good, right? Then the nuclei start to repel each other. And so when you're here, when you're up here, if your average internuclear distance is up here, then you're too close. Or your energy of interaction is up here, you're too close. You're hitting too hard. There's no attraction. You're hitting too hard, and you're in a pressure regime that is not favorable. If you're down here in this range, that's great. So this is an attractive range here. And this is repulsive. And this is an average thing. So if your average interaction is repulsive, then when you expand this gas, it's going to give off heat because it's got too much heat that it's got all these, it's going to relax. It's going to be like, finally, I'm out of that situation and I'm going to get rid of that excess energy that I had. So it's got excess energy that it needs. If you're down in this attractive region, it likes it. So in order to expand that, I've got to pull those molecules apart. And I can't pull them apart without giving them energy or the temperature dropping. And so this inversion in the Joule-Thompson coefficient depends upon this break here, whether you're in a repulsive region of pressure or an attractive region of pressure. So we could go back and look at that chart, and we can see how in that gray area, we're in the attractive region of pressure. Outside that gray area, we're in the repulsive region of pressure. Molecules are hitting so hard, they don't ever feel the attraction. And in fact, if they're really hitting hard, if you got a really high pressure, they're relieved when you let them expand. And they can't just be relieved. They've got to get rid of that excess energy. And so that excess energy comes out in terms of temperature. Now, this is the nature of refrigeration. This is your basic refrigerator. You have a compressor. You compress the gas. When you compress the gas, it heats up. And so you have a heat exchanger somewhere, a lot of times on the back of your refrigerator, and you get rid of that compression heat. So you get that gas back down to room temperature, and then over here, you run it through this little pre-cooler, and then you expand it. So this is the expansion nozzle. And sometimes it expands and cools so much that it liquefies. And so then you have a liquid gas in here, and then you put your ice tray in there. This is an ice tray, okay? And you got a little water in your ice tray, and that water is giving off heat. And those little photons of heat and so on hit this thing and cause a little molecule to evaporate. And that molecule evaporates and goes back to the compressor. And so it's this piece right here, this expansion piece, that uses the Joule-Thompson coefficient to tell you how much that gas can cool with the change in pressure. So if you have a really high Joule-Thompson coefficient, the temperature is really going to drop when it expands. And things that have high intermolecular attractions are really good refrigerants. Now this is really bizarre. We use a compressor, but in the RV, you can do anything that creates a higher pressure, like raise the temperature of something. And so in our RVs, we actually have flames. You can light a propane flame down here, and instead of the compressor, you use a flame. And that heats up the gas, and it goes up in here, and so then this gas is heated up here, and you can create pressure with heat, and that gas goes out here and gets rid of its heat, and essentially I'm using a fixed volume and a flame in terms of to replace the compressor. It doesn't seem like it would work, but it works. I always was amazed at that when we go camping and we had a propane refrigerator. That's weird. I light propane and I can turn my water into ice. And it's using the Joule-Thompson coefficient. So that's a really clever use of thermodynamics. And this is an Einstein Refrigerator. So they came up with this patent on refrigeration. They used ammonia. A lot of intermolecular attractions with ammonia because of the hydrogen bonding. And they were bothered because there was a Berlin family that was killed when the seal in their refrigerator broke and the ammonia got out and it killed them. And so then they came up with a better design that wouldn't leak. So anyway, that's the connection to Einstein and refrigeration. That's pretty much it. So I'll see you all next time.